Hi, I'm Paul. We are doing Leetcode must-know interview questions. Today's challenge is coin change. So let's say you are given an integer array coins representing coins of different denominations and an integer amount representing a total amount of money. Return the fewest number of coins that you need to make up that amount. If that amount of money cannot be made up by any combination of the coins, return -1. You may assume that you have an infinite number of each kind of coin. Okay, let's look at an example of how that would work. All right, so let's say you have coins of denomination 1, 2, and 5. You want an amount of 11. If you give back 2 5s and a 1, that's 3 coins. That's the best you can do with that. Let's say you have you want an amount of 3 and you have 1 coin, denomination 2. Well, in that case, we got to return -1 because there's no way to make that amount with that coin. If you want an amount of 0, it doesn't really matter what the coins are. We're going to return 0. Constraints are coins. We can have coins up to 12 different denominations. The amount of the coins can be between 1 and 2 billion. The amount will be somewhere between 0 and 10,000. And yeah, the rating is medium. Now, you might say, well, yeah, but I've seen this problem before, and it's just a greedy algorithm. You just give back the biggest number until you can't give back a number anymore. Like this one, you just give back 5s, 5 and 5, and then, well, I can't give a 2, and so I give 1, and that's it. That doesn't really work in this case. It works for regular money like pennies, nickels, dimes, quarters, because of the way they relate to one another. But if you had here, we'll give you some numbers. Let's say you have the number 9, you have the number 8. Those are your coin denominations, and you want an amount of 16. Okay, here's the greedy approach. Give back 9. I can't give back any more 9s, but I can't give any 8s either, so I'm stuck. What you really want to do is you want to give back 2 8s. So a greedy approach to this is not going to work. Where's the eraser? What we need is a dynamic programming approach. Let's take a look at how that might work. All right, what do we need to keep track of here? One thing that we need to keep track of is, well, I say keep track of, it's just that because they're not visible here, let me write down the denomination of coins. This is, for example, 1 coins. We have 3 coins. We've got a 1, a 2, and a 5. Okay, we're going to need a loop index. I'm going to call that I. And what else do we need here? Well, we need the amount. We already know that it is 11. We need a DP array, a dynamic programming array. I'm going to go ahead and pause this while I draw it, and then we'll come back. All right, so here's the DP array for this. The length of the DP array is amount plus 1, so we have an array here of length 12. The significance of the DP array is that DP at any index I is the minimum number of coins that we would need to return this amount of money, I amount of money. Well, the only one that we really know to start with is if the amount is 0, then the number of coins that we would return is 0. Now, what we do at this point is we take the coins one at a time. The first coin, well, the first coin is 1. Okay, and we start the index at 1. We start the index at the coin value. And we look at DP1, and what we want here is we want the minimum of either what's already in there or what is at, we have to compute a new index, and that new index is the index minus the coin value, which in this case is 1 minus 1. It's 0. Take that amount and add 1. And 1 is less than 12, so in this case, what we want is not 12, but 1. So that makes sense. You know, if we can return 0 with 0 coins, and we have a coin with denomination 1, then we can return 1 with 1 coin. All right, now we would do it again. We would increment the index. The index is now at 2. So we go to 2, and what we want here is the minimum of what's already there, or compute a new index. Index minus coin value. It's 1. So we'll look at DP1 and add 1. Is that less than 12? 1 plus 1 is 2. Is that less than 12? Yes. So we don't want 12 in there anymore. What we want is 2. Okay, this one is pretty simple. You can probably see that what's going to happen here is we're just going to fill in 1, 2, 3, 4, 5, etc. all the way across the board here, because that is the minimum number of coins that we could return with a coin of denomination 1 for each amount. So I'm going to pause this for a minute and go ahead and do that. All right, so that's what the DP array looks like with a coin of denomination 1. For each of these, this is the minimum number of coins that we would need to return for each amount. Okay, let's go to the next coin. Go to coin 2, and we're going to start the index at coin value. All right, so we'll look at DP2. What we want in there is the minimum of either what's already in there, or we compute a new index, which is index minus coin value, 2 minus 2. We look at the value there, that's 0, in DP 0, and add 1. And 1 is less than 2, so that means we got to change this. This is not 2 anymore. This is going to be 1. Well, that makes sense, because if we now have a coin with denomination 2, and we can return 0 with 0 coins, then we can return 2 with 1 coin. All right, let's increment the index. 3. What do we have in 3? What we have in there now is 3. If we compute a new index, index minus the coin value, 3 minus 2 is 1, and we look back here, we have a 1 there. If we add 1, we get 2. That's actually less than what we have in there now. So that has to become a 2. If we can return 1 with 1 coin, then with a coin of denomination 2, we can return 3 with 2 coins. All right, so I think you can probably see here what's going to happen as well. The 4 is going to change to a 2, the 5 is going to change to a 3, and again, I'm going to pause it for a second while I propagate that through the array. All right, so that's what the DP array looks like. If we have coins of denomination 1 and 2, we are going to add a coin of denomination 5 and see what happens. The index starts at the coin value, All right, so we can look at the index at array 5. It's currently 3. We're going to compute a new index. Index minus coin value, 5 minus 5, it's 0. We look at DP 0, and it is 0. If we add 1, it's 1. Is that less than 3? Yes. To avoid erasing, I'm just going to write the new number. I'm going to write the new number up here. Really what we're doing every time as we increment the index is just going through the rest of the array and looking back 5 cells, 5 being the denomination of the coin, and adding 1 to that and seeing if it's less than what's already in the cell. So from 6 we look back to 1, add 1, and we get 2. From 7 we look back to 2, add 1, and get 2. And again, it's because we can already give back. We already know that we can give back an amount of 2 with 1 coin. So what about 7? Well, now we've got a coin of denomination 5, so we can just add the 5 to the 2. 8, currently 4. If we look back, 3 is 2. Add 1, we'll get 3. 9, look back. 5, we get 2, add 1, and we have 3. 10, look back. 5, and actually we have 1. So for 10, we only need 2 coins, and for 6, look back. 5 at the 6, it's actually not 3 anymore, it's 2. And so for 11, we can give back 3 coins, and that's the answer that we're looking for. And it really doesn't matter even what order the coins are in, that they don't have to be in ascending order. We could start with the 5, for example. We'd go through it the first time. This index here, the 5, would be a 1. The 10 would be a 2. We wouldn't find anything less than that as we started to go through the lower denomination coins, and when we got down to the 1, we would realize that if we can give back 10 with 2 coins, then we can give back 11 with 3 coins. How do we know if this doesn't work, by the way? It doesn't work if we're unable to get to the final cell in the array. For example, if we have, well, you know what, I might be able to sketch that quickly. All right, this is what the failing example looks like. We have an amount of 3 that we are trying to get, and we have 1 coin, denomination 2, so we start the index at 2, and we look to see if we can compute the new index 2 minus the coin value 2. Again, basically we're looking back 2 cells and adding 1. Is that less than what we have there? And it is. So we can change that. We don't need 4 to give back 2. We only need 1 to give back 2. But then we increment this, and I'm sorry, we increment this 3. We look back 2 cells, we increment it 1. That's not any less than what we have. All right, and now we're done. If you get all the way through and the number in the last cell is equal to amount plus 1, which is what we initialized it with, then we have failed and we have to return -1. Okay, so let's look at an implementation of this. All right, so let's handle the edge case here, which is amount equals 0. If the amount equals 0, we'll go ahead and return 0. The algorithm would actually handle this correctly. We would just have to, loop through the coins. Arrays. We are going to fill the arrays. Fill the array. Oh, wait a minute. Why don't we declare the array first? Got an integer array. We'll call it BP. equals new int amount plus 1. And then we will fill the array with from 1, whoops, not DO, BP. The cell at index 0 should be initialized to 0 already. It's the default for an int array. So we'll go to 1, from 1 to BP dot length, and fill it with amount plus 1. All right. For each coin in coins, we'll run the index for int I equals coin I less than or equal to amount I plus plus. We want dp at I to be the minimum of whatever is already in there, and dp at index minus coin value plus 1. Okay. Return. We've got to check something first. We've got to check whether dp, it's not a square bracket, is it? dp amount equals amount plus 1, because that is an indication that we didn't get there. It's still initialized to the amount plus 1 that we put in there to start with. In that case, we failed. We return -1. Otherwise, we return the dp amount. All right, is that it? I think that's it. Let's try and run it. Accepted. All right. Move this back over here. Submit. Study plan, no. Okay, good time. What is the runtime here? It's well, let's see. It's the amount times the number of coins. I don't know how they would express that. I mean, it's really not n squared. It's m times n, but we didn't really identify anything as m or n here. Let's see what they have to say about it. N times v. Okay, fair enough. I don't know what they're calling n and v, but it is number of coins times amount. I guess n would be what? Number of coins, and v would be the... I don't know. Okay. What would they call n? I guess n would be... it would probably be amount is n, and v for vector is number of coins. So let's go with that. Anyway, that's a good solution. Mm, hope you enjoyed it. Please feel free to like, comment, subscribe, and see you next time.